Hey, Transformer, Transformers, robots in disguise. Did you watch the really old Transformers? জন্মের আগের ট্রান্সফর্মার গুলো
না
কার্টুনের মতো মানে কার্টুনেই নট কার্টুনের মতো কার্টুনই ছিল লাইক ইউ নো মানে they had this weird sound like করে তারপর পাল্টায় যেত the transformations were like really cat compared to like you know now yeah Transformers but yes hey look it's Samin Sabah ওরে ওই একটু আগে দেখে আসছি একটু আগে like you know thanks for doing this even though you've had a very hectic day. Oh, that's so sweet. Like you know, but like you know, I don't know. Yes, I remember. I think he's talking about the old Transformers. Transformers. Cool stuff. Okay, we should start, yeah? Okay guys, we have a lot to study today. We'll have to study a lot about... Oh look, it's Masroor again. Like, you know, I told you about Masroor.
Oh, how would you?
Like,
Live.
Yeah. Are you Rahul? Or Rahul? So like, yes, I am. You know, I don't know, come on a bit. It's really cool. And yeah. So today we're going to be talking about elastic collisions and momentum. No, not momentum. First, relative velocity. We'll talk about relative velocity and also collisions. All right, let's get to this. So say we have a basketball and we allow it to hit the ground, right? So এরকম bounce করলো. So what do you see in real life when a basketball bounces off the ground? What would you see? So say a ball, it bounces back up, but will it bounce back up to the same height? No. So it bounces like this, then bounces like this. This is what is normal, right? So this is what we usually see in these sort of collisions, is that when they hit the ground, they bounce back, but not to the same height. Can you tell me why? So what happens here? Why does it bounce with less and less height?
It's energy loss.
Yes, very good, because energy is lost with each collision. So these sort of collisions are called inelastic collisions. Really easy stuff, right? So it's called an inelastic collision because fundamentally you lose kinetic energy. Please remember, it's got nothing to do with momentum, right? So basically, eta je height theke jump korlo, inelastic collision hoilo. How can you know that this is an inelastic collision? What's the easiest way of finding out that this is an inelastic collision? Any ideas?
Speed of approach or
Yes,
separation.
very good. Very good. You're pretty good at this. So we can call this the speed of approach, and eta when it goes away, we can call this speed of separation, right? Approach and receding velocity, right? Well, let's just use simple English. So we know for a fact that it's lost energy here. That's why it's going to separate at a lower speed. Bucho. Because if it hit here, J kinetic energy at J speed niye hit korbe is going to bounce off with less speed. And there's one fundamental proof in this. Proof is basically the height. Say this is h1 and say this is h2. So basically h1 is more than h2, which means what? It lost GPE. So that means also during the bounce, it lost kinetic energy, right? So এই জিনিসের কারণে speed of approach or speed of separation যেটা আছে, they're not going to be equal. And that is basically the definition of an inelastic collision. So inelastic collisions are defined as collisions in which, number one, kinetic energy is not conserved. Number two, speed of approach, তাহলে if it's not conserved কি হবে? speed of approach will obviously be greater than speed of separation. Well, it's going to approach faster compared to when it bounces off the ground again. All right, this is this scenario. Now, let's consider a different scenario. Another scenario would be, say for example, we take this to represent the ground, and we have this special sort of crazy ball, and what the crazy ball does is basically it bounces and comes back to the same height, right? So eta to the phi, have you ever seen anything like this? Have you ever seen any sort of collisions? No. Why? Because these are not collisions that we see happen. They don't actually happen that much. So these sort of collisions are actually called elastic collisions. And why are they called elastic collisions? Because fundamentally what's going on is that the collision is not making any energy being lost. And how do we know that there's no energy lost in the collision? Easy. Because
it bounces back to the same height.
Very good. Mystery students, really smart. So H1, H2, these values, even if we take H3, these values are all the same. So this collision right here, this is an elastic collision. Sometimes you will see it's written as perfectly elastic collision, right? Doesn't really matter which way it's written. Collision's a collision. So we have elastic collisions. And what would be the properties of elastic collisions? Could you tell me? Based on what we just compared it to.
Kinetic energy is conserved.
Yes, Ke is conserved.
And speed of approach is equal to the speed of separation.
There's a different way of also writing K is conserved. You could say that the kinetic energy before collision is equal to kinetic energy after collision. And yes, kinetic energy before collision is greater than kinetic energy after collision. Well, not equal to. And yes, speed of approach is equal to speed of separation. Right? Pretty easy, pretty simple. And we identify it easily here because the height to which it jumps is the same. So inelastic collisions, and we have elastic collisions. Really easy, really simple. Now, out of here, there's a couple of questions that I'd like to ask you, which I would like you to answer. The first question is, do you think there's anything to do with momentum with these collisions?
No.
No, right, that's correct. That's very good. So, do you, regardless, if a collision is inelastic, kinetic energy is not conserved. Do you think the momentum is conserved?
It is.
All right, very good. And what about in elastic collisions?
Same.
It's also
Conserved.
conserved. So that means what? It doesn't really matter if a collision is elastic or inelastic.
Momentum is always conserved.
Yes, you're so smart, man. You're really smart. So that's a very important thing about these sort of collisions. So we could actually turn this into a short, small table, right? So elastic collision, and inelastic collision. All right, moving on. So momentum কি হবে? এখানে elastic collision conserved, inelastic collision also conserved, right? Momentum এর পরে কি আছে? Kinetic energy. Elastic collision conserved, inelastic collision not conserved. And then we can talk about relative velocities. এখানে elastic collision speed of approach is equal to speed of separation. Inelastic collision speed of approach is usually greater than speed of separation. So yes, there we go. So these are the different scenarios that you have to remember. All right. Anyway, moving on. So this is basically the fundamental idea behind elastic and inelastic collisions. I hope that's clear to you and everyone. Naki. Okay, so let's just quickly review this before we go on to the next concept. So collisions can occur in two different ways. They can either cause a loss of energy in the collision, or they can cause no loss of energy. In real life, almost all collisions are inelastic collisions. Theoretically, you can have only perfectly elastic collisions on a subatomic level, like alpha scattering and stuff. But even then, if you were to specifically look at it, in certain perspectives, it is also inelastic. So it's a theoretical sort of situation, number one. Number two, inelastic collisions will always have a greater speed of approach and a smaller speed of separation. And in elastic collision, speed of approach and speed of separation both will be equal. Right. And under all situations, momentum is conserved. So it's really easy, really simple. So the thing is, they're not going to ask you questions like these. এরকম যদি simple questions জিজ্ঞেস করতো তাহলে তো হয়েছিলই. The thing is, they're going to ask you questions which are a little more complex. For example, you might have two masses approaching each other at certain velocities, say v and v. This is minus v. So they have equal masses m and m. So they're going to collide and everything. What?
M&M.
M&M. All right. So, okay, we'll get M&Ms next class. We'll have M&Ms. So the total momentum of this is going to be mv plus minus mv. So we do use the minus because momentum is a vector quantity. So it adds up to how much? The total momentum of the system is 0. So after they collide and after they move apart, you have to conserve momentum. And if it's mentioned that this is a perfectly elastic collision, then you also have to conserve the relative speeds. So there's no point trying to find out separate kinetic energies and everything, blah, blah, blah. Even though there is a way of doing that, it's easier. You just see the relative speeds and see if they add up or properly or not. For example, if one of these were stationary, it would be like this is approaching it at a velocity of 2v, right? That's how we find relative velocities. Basically, relative velocity is a difference. So you subtract one from the other. So that would be the relative velocity between the two is going to be v minus v. So that's basically 2v. They're approaching each other at 2v. That's one way of looking at it. This is considering the convention that moving towards each other is a positive value. If you said like, why not minus v, then that is basically you're considering the convention of moving towards each other as minus 2v. So whichever way you consider it as, they approach each other at a velocity of 2v. So the momentum is being considered to be 0. And when they collide, they have to move away in opposite directions, having no resultant momentum. So there's two possibilities for this. One possibility would be that this is going to be moving away at minus v and this is going to be moving away at v, right? And this conserves the whole scenario. Momentum is conserved and also the collisions are perfectly elastic. There's another possibility or another scenario, but that doesn't actually happen because you have to conserve momentum. So if, for example, if you were to say we didn't have this as the starting, we can create a different scenario. So we have one mass of m and another mass of say 2m, and this approaches this at a velocity of minus v, and say this is stationary, all right? So the velocity is 0. So when they hit each other, before they hit each other, what's the total momentum of the system? It's minus 2mv, right? And when they hit each other, usually what we're going to see is this m will move forward and this will also move forward. Usually the one with more mass dictates the direction in which everything's going to move. So because this has more mass, it's moving in this direction, everything's going to start moving in this direction. That's basically the concept of pool and snooker. Have you played pool and snooker?
Yeah.
Okay. So in pool and snooker, you've played with the cue ball, right? The white ball. So the cue ball is obviously a little heavier than all the other balls. So that's why, like, you know, if you hit it, if like, you know, there's a ball and you hit it with a cue ball and it moves, this continues to move in a specific direction, and this may move, or even in this direction it's going to move. And it's partly due to the ball rolling over the surface of the table, but it's also because this is slightly heavier than all the other balls, right? There's a lot of physics in snooker, like, you know, a lot of people don't know that, but it's pretty cool stuff. So yes, in this situation, what would it be? If we were to say that this collision is also perfectly elastic and speed of approach is basically minus v, then this has to move with a velocity of 2v, right? And this can move with a velocity of v. That's one possible scenario. But there's a problem here. The problem is we're not conserving momentum, right? So basically we'd have to come up with an equation to find this momentum. But before we go into more detail of this, I need to talk about one other specific concept, which is relative velocities. So relative velocities, as I mentioned a few moments ago, it's something that it's the difference between two. So whenever we find total momentum, we add values, but whenever we find relative velocities, we always subtract values or find the difference between the two. So say this is moving at 10 meters per second, the mass moving, and this mass is moving in this direction at 15 meters per second, right? So they're approaching each other. What is their speed of approach?
5.
No, the minus here.
Actually, so minus 5.
Yes, because the direction is different. No, it's not minus 5. It's going to be basically...
Oh, sorry. That's by now.
That's not a good excuse, but like, you know. So what's going to be the scenario is if we take this direction as negative, that we've done here. So the sum, or basically the relative velocity, the difference between the two, is going to be 10 minus 15. So that's basically 25 meters per second. So that means they're approaching each other at 25 meters per second. All right? Now, let's take the same scenario and look at it a little differently. Say they bounce into each other and then they move away from each other. So say this moves away at 5 meters per second. If this was a perfectly elastic collision, what must this velocity be? Okay, I'm not going to ask you. Okay, can anyone tell me what's going to be the value for this specific collision? Anyone? So speed of approach is 25. If it's a perfectly elastic collision, then the speed of separation must also be 25. So this moves with the velocity of -5 in this direction, then this must move with a velocity of 20 meters per second, so that they're separating at a speed of 25. They were approaching at 25, they must separate at 25 also. Right? Do you get that? Okay.
But like, what about the minus the?
Yeah, minus the a direction now.
Yeah.
And তখন তুমি যদি ক্যালকুলেশন করো তুমি দেখো, notice this, তখন আমরা বলছিলাম কি 10 minus minus 15, right? তখন এটা যাবে -5 minus 20, so basically minus 25. So that shows what? That whenever particles are approaching each other, we can consider in this scenario, in this specific scenario, when they're approaching each other, it's a positive value. When they're moving away from each other, it's a negative value, right? So we can take this a little further and see slightly different situations and scenarios. And that would be, say, for example, we have a mass moving at, say, 10 or 15 meters per second, right? And another mass moving in the same direction with 10 meters per second. So are they going to move towards each other or are they going to move away from each other?
Right, they have the same mass. Right, they have the same mass.
That doesn't matter.
I don't know, maybe
No, just this scenario right now, before any collisions or
that's
anything.
my left, towards the left necking.
So yeah, they're moving in this direction.
Right.
So are they going to move towards each other or away from each other before colliding?
Oh, before colliding.
Will they collide? Basically, that's the question.
Yeah, they will.
Why?
Because this will catch up to that one.
Yeah, exactly. This will catch up to that. At what speed do you think this will catch up to this? Easy. 15 minus 10, basically 5 meters per second. If you were basically sitting on this or standing on this, you would see this ball approach you at 5 meters per second.
All right.
Right? Easy peasy, man. Easy peasy. So yes, that's basically what you would get. And etc. It will 15 and 10 meters per second, right? And yeah, there you go. Sadia says 5. So one more scenario, then we'll be done. Is, say, for example, what about this? Say this is moving at 3 meters per second. Oh, by the way, once they collide, if they move apart, what will their velocity have to be? Separation?
-5.
It has to be. Excellent. It's going to be -5. So say we take another scenario, 3 meters per second in this direction, and we have another ball which is traveling in this direction at, say, 9 meters per second. So what's their relative speeds?
So that's 3 minus 9.
3 minus 9, which is equal to -6. So they're not going to even collide. They'll just move apart at a speed of 6 meters per second from each other. But that... Alright, so this is the very basics of the introduction of relative velocities and everything. And that's the basic idea of it. I guess that does cover most of the scenario that we need to know about. Okay then guys, good night, take care, and enjoy. Fun teaching you guys.